right, welcome in everybody. Oops, are we getting an echo over here? Nope, we're good, I think. Okay, great. I will take roll in a few minutes, give people a few more minutes to come on in, and then we'll go from there. So let's see, where are we? At a holiday last week. So, you know, when you're in a class that only meets once a week and then there's a holiday, it seems like forever since we met. So hopefully you continued. I know many of you did continue working and progressing and moving ahead. That's great. So we'll continue. We kind of have to in this course, right? It's like I say, we gotta get through all the algebra, and then it lightens up in the second half of the course. But we kind of have to get there first. We have to get to that point where we can make things a little bit easier. So, right. I would say anyone who's considering dropping the course, please talk to me first. There's stuff going on with the courses right now, which may make it inconvenient for a while. As far as this course, I'm not supposed to talk about the future of this course because nothing's been decided yet. But you just talk to me before you drop the course. There may be some considerations. For those of you who are not considering dropping the course, just keep plugging along and doing what you're doing. But anyone who's considering dropping the course, please talk to me first. Right, so we are, let's see, a couple things I wanted to mention here in Canvas. So I will be showing you quite a bit of math today. So I know there's 10 of you right now on the YouTube stream. Probably a good place to be because you're gonna be seeing a lot of stuff. Okay, so one thing I want to point out, I added a discussion, right, in the Systems of Equations chapter, which I believe all that homework is due today, so you're wrapping it up. You have until the 7th here to complete this, but it's one of the requirements for our online courses is we have to be giving students an opportunity to interact with each other, so discussion boards, that kind of stuff. So this is a graded assignment. It's not very difficult. Just go in there and answer the question. So the prompt is, please explain something that helped you understand the problems in this chapter better. So basically, were you struggling and then you learned something and then all of a sudden it was like, oh, I get it now. Share that thing that you realized that helped you figure it out. Was there a technological thing that you figured out? Was it how to answer the questions inside of Delta Math? Anything that you were having trouble with, and then you figured out how to do it, and it made the chapter easier, go with that. Just put that up there, right? And so, as always, low effort comments won't get points. Things like I agree or good point or something like that. Doesn't really add anything to the conversation, right? You can put those things up there. That's fine. If you want to give someone some encouragement, like go for it. But in order to get credit, I'll have to see at least one comment that's like, meaningful, adding something in some ways, okay? So, right. So just be aware of that. That's up there. It's easy 10 points, right? Those end up going into the homework section. And we've got, let's see, where are we here with modules? We are now beginning. Oh, nope, that's not true. I was about to jump the gun. We got a few more things to go through. So we've got, let's see, we've got this chapter we're starting today. Then we have to get through quadratic equations, and then we have to get through logarithms. The logarithms we won't really use much in this course, but some of you need to take chemistry, and you do need to know how to do logarithms for chemistry. Okay, let's see. I'm getting a couple messages here. Let me look. Oh, okay. Okay, good to know. Okay, so we're going to be looking at this chapter on radicals and exponents. Hopefully you're almost done with this systems of equations stuff because it's, like I say, I think it's due today. Oops, that's not. This is the one. Yeah, February 28th. A lot of that stuff's due today. So make sure you get help with that so you can get all those points. We are moving ahead into this chapter. this chapter that's titled Radicals and Exponents. What does that mean? What's a radical? Radical is just like it's the formal name for the square root sign. You know, when you see a square root, that little symbol, that's called a radical. So it's, you know, it's nothing intimidating or scary. That's all it is. But the thing about this chapter is there's a ton of little details that you have to keep track of, right? I would say up until you get to radical equations, most of the problems you do are fairly simple. Now, sometimes people get confused with that language. When I say simple, that doesn't mean easy, right? Simple doesn't mean easy necessarily. Simple means not complex. In other words, most of the problems that we do in this unit aren't terribly complicated. They don't have a ton of steps. You just have to remember how to do them. And there's a million different types of problems that you can run across, and they combine with each other and they overlap, and you just have to remember all these rules. So really the approach here, especially for this chapter, I mean math in general, but especially this chapter, is you should not be trying to memorize things. You should be trying to understand things, because this is one of those chapters where you really want to bring your toolbox when you're trying to solve problems. You don't, like, if you're trying, like, you just can't memorize how to do all of these problems. There are so many different variations and so many different versions of the problems. You're not going to memorize them all. What you want to do is have a basic understanding of how to do certain types of problems, but that underlying understanding of how to do them is going to be beneficial to you. So, for example, the first thing, and I don't have time to cover this in class, but the first thing is all those rules of exponents, right? Remember all those rules from whenever the last time you took algebra was. For some of you, that was high school years ago. For some of you, it was, you know, high school a year ago, or, you know, some of you may have taken a class at VC. We're not really supposed to offer just straight algebra courses anymore. Because the state restructured how math departments are supposed to work at the community college level. But at some point, you learn some rules of exponents. You're going to need to know how to use those, because what we are doing is more advanced rules of exponents. So if you don't remember the basic rules of exponents, you can't do the advanced rules of exponents. So I've got some videos in here that you can watch, right? A lot of videos, and you might go, oh, that's an overwhelming number of videos. Remember, most of these videos are like a few minutes long. Like 2 minutes, a lot of them. So, you know, even if you watch 10 of them, that's only 20 minutes a time. So it gets through a lot of the rules of exponents. So if you're a little bit rusty on how all of that stuff works, you can remind yourself. So just watch the videos and you should be fine. And then we're going to be getting into more complicated rules of exponents. Okay. Oh, that's funny. The green bar. The band to be on campus today is green, so it's matching my green screen. So my hand is sort of floating all by itself. It just distracted me when I saw it doing that. Hopefully you remember how to deal with positive style exponents, and then I'm going to be showing you, I'll do a real quick reminder here, but we'll get into the negative exponents and then specifically the rational exponents. But before I do that, let me take roll. So I think we've got people are pretty on top of putting their name in here, which is great. So let me go through. Give me a few minutes to take roll here. Okay, thanks for your patience there. We got that done, so we can get that out of the way. Okay, so we are getting into this chapter. There's videos posted on the website. So, okay. I think I got. So there's videos posted in Canvas that you'll want to watch because remember, we're like, at this point we have a little more than an hour of today's meeting, and I just can't get through everything we would have to cover. So make sure you're watching the videos that are here in Canvas, and then I would encourage you to watch the videos that are on the Delta Math, right, that are part of that. So between those, you should be able to get through all of them, like the radical equations in here. Just these are different types of radical equation problems you're going to run across, but I've got videos to work you through all of them, and I'll show you the hang-ups where people usually make mistakes. Like with the equations one, if people are doing pretty good, there's like one mistake that they usually make consistently, and then they kind of drive themselves crazy trying to figure out what they did wrong. So we'll talk about that when we get that far, but there's a ton of little things along the way that we want to pick up and talk about. So let's see. We were looking at, you've got some exponent stuff coming up. So fractional exponents coming up. Oops, kind of off the screen there. You've got fractional exponents coming up. You've got negative exponents. You probably saw negative exponents before at some point, but you might not remember them. That's okay. We'll relearn them quicker. Some exponent practice in general. Right? And then simplifying radicals. This is where we really get into how do we actually use these things and simplify them, and then how do we solve equations with them down here in the radical equations. So you have a little over a week to do that. Many of these problems are very short. So some of these you might look at and go, that's a ton of problems, but some of them take a minute to do, right? So you'll move through them pretty quickly, hopefully. So let's start off with some information I can give you, and then we'll get into stuff. I think I covered everything that we need to cover. Remember, and it's still weeks away, but remember when we transition from the algebra portion of the course to the math for meds portion of the course, there will be an exam at that point, roughly in the middle of class, probably a little bit after the middle, maybe a little bit after the middle of the course. And we'll go from there, okay? So let's see, where are we? This is what I'm looking for. I want to write some stuff. Let's shift this over to here. Sorry, I ate a little bit of chicken right before class, and then eating lunch always makes me like drowsy. Okay, so, but I need this where I can write on it. Okay, so what are we talking about with radicals and exponents? So we have our basic rules of exponents, and you're going to have to be comfortable with this because you're going to have problems where you have to simplify using exponents, and you're going to have to remember how those work. So let's do a real quick overview of those. There's videos in Canvas that I've posted for you, but two of the big ones, if we have a to the m times a to the n, then we need to know how to simplify something like this. And it turns out we can kind of do some problems to motivate, like figure this out. So when I say don't memorize things, think your way through it, students mix up the rules of exponents all the time because they're trying to memorize, when do I add exponents? When do I multiply exponents? When do I do all these different things? And you try to memorize it. You have no context. So when you remember wrong, you don't know that you're wrong because you don't really understand what's going on with the problem. But if you understand, then you'll be able to make sense of why you're doing what you do, and then you're much more likely to make the right decisions. So in other words, how would I make the decision here? Usually the question for students that they have is, I kind of remember, but I don't remember if I'm supposed to be adding the exponents or if I'm supposed to be multiplying the exponents. That's where students usually get kind of confused, adding exponents or multiplying them. So what you can do is you can make yourself a little example and figure it out. So let's say we've got x squared times x cubed. right? That would be an example of a to the m times a to the n. We're doing a specific example of x squared times x cubed. Now, what would I do with this? I'm trying to figure out, I wonder what would that be? Well, let's play around with it. X squared means x times x, and x cubed means x times x times x. Okay. So we can kind of see this first parenthesis makes sense as an x squared. This one is x cubed. Well, what do I really have here? I have 5x's multiplying together, right? So this really should simplify logically to x to the 5th. And then I go, oh, okay. So x to the 5th, that must be the case where I added those exponents together, which also makes sense because this 2 means I have 2 x's here. This one means I have 3 over here. Altogether, I have 5 x's. It makes sense that I would add those exponents together in order to simplify this, right? So x to the 5th. Okay. So that means we're adding these. That means our rule up here is a to the m plus n. Okay, that means we're adding those exponents together. So you did a little bit of this when we did factoring and you did polynomial multiplication. Remember, we were kind of using rules of exponents back then. We're using it again. When you multiply exponents, that's a different situation. That's when we would have the case like x squared cubed. So see how we're raising, basically we're raising an exponent to an exponent. In this case, you go, okay, well, what would I do there? Well, x squared cubed really means x squared times x squared times x squared. And according to the rule above, we should be able to look at that and say, oh, I think I'm supposed to add those exponents together. In this case, you know, at this point where we have it spread out, I should add the 2 and the 2 and the 2. I don't add these together, but here I add the 2 and the 2 and the 2 to give me x to the 6th. And then we look back at the beginning and go, oh, I'm supposed to multiply this. The 2 times the 3 gives me the 6 back here. So see how you don't have to memorize them? If you're able to just make yourself a simple example and you work your way through it, you can remember, you can like remind yourself what's the proper procedure there, right? So we won't go through all of these because we have to get into the actual algebra that we're looking at. So we're going to talk a little bit about square roots, and then depending on time, we may circle back, hopefully, to these rules of exponents. It depends how far we get. You might be getting it from videos, so you'll have to watch the videos when we get to that point. But what we have with square roots is we have this thing called the principal square root. Okay, now the definition that we give you sounds confusing for roots, right? It's like, I know a lot of times in these classes when we define something, people are like, you're making it way more complicated. There's a much easier way to think about that. Well, the reason in mathematics that we make complicated definitions for things is because down the road, when you get into more and more complex problems, you start to run into cases where you go, well, I don't know if this definition applies anymore. How does it fit this particular problem that we're working on? And so that's why we write very specific definitions, because then even when you're in a really confusing problem, it'll be clear if the definition is supposed to apply or not, right? But it can work against you in the beginning when you're trying to get a sense of, you know, when you're first learning the problems, it can make it a little bit confusing sometimes. So basically what we have is, we can say that, let's see, I'm going to try to paraphrase this definition a little bit here. Actually, I guess that's my other book I'm thinking of. This book doesn't seem to even have a good definition. They don't even define it anywhere. Okay, basically it goes like this. So if b squared is equal to a, and we have a little side note here. And b is greater than 0, then b is said to be the principal square root of a, and that's spelled wrong. And we write this the square root of a equals, well, let's write it this way, b equals, and this is not fitting on the page, so let me change my type size. And we'll shorten this a little bit. Okay, so if b squared is equal to a, and b is greater than 0, then b is said to be the principal square root of a, written b equals the square root of a. In other words, when you multiply b times itself, you get a. That's what the square root means. Now, what's this bit about the principal square root? We don't usually say that, but we mean it. So what happens is, technically, we have two situations here, right? So here's an example of what I'm talking about. We could say that 3 times 3 equals 9. So the square root of 9 equals 3. Right? This would be an interpretation. 3 times 3 equals 9. Or you could say 3 squared equals 9, however you want to write it. 3 times 3 is 9, so the square root of 9 is 3. Okay? But we have to be careful here, because we could also say, well, can't I just say that negative 3 times negative 3, that equals 9 too. So can't I say that the square root of 9 equals negative 3? And the answer is no. So when we talk about square roots, we specifically want the positive one. And so even if negative 3 times negative 3 equals 9, that's not the one that we want to deal with. So the principal square root is technically the positive one. We don't want to deal with this kind of thing right here. So the second line, ignore that. And most people just call it the square root, but every once in a while you get into the details where you kind of have to remember this specifically and sort of make sense of it. So for instance, we can see some problems like this pretty easily. So the square root of 36, well, I ask myself, what number times itself gives me 36? Well, the answer is 6. So the square root of 36 equals 6. That makes sense, right? That's all reasonable. Okay. Well, what if I wanted the following? What if I wanted to talk about the square root of negative 36? So I'm asking myself, what number times itself gives me negative 36? And here we run into problems. Oops, I got to scroll up a bit. Here we run into problems because a number times itself is always positive, right? If we're talking about real numbers. The complex numbers are different, but we're not getting into complex numbers in this class. So if you want to work inside the complex numbers, that's a different story, but I don't believe that's going to come up in our dosages and stuff like that. Complex numbers, they make sense in very specific areas, electrical engineering, physics, chemistry, some stuff like that. But complex numbers I don't think are really going to come up in dosages and things like that. So we don't have to worry about complex numbers, which means we'll be living in the real numbers. And there is no real number that when you multiply it by itself, you get negative 36, because a negative times a negative is a positive, and a positive times a positive is a positive. So either way, if your number is positive or negative and you multiply it by itself, you get a positive number. So what we will do is respond to things like this by saying not a real number. And be careful, when we say not a real number, we mean specifically it's not part of the real number set, right? The set of real numbers. A lot of times there's like a judgment where people go, oh, it's not a real number, it's just some made up fantasy thing. No, like complex numbers are perfectly valid. We wouldn't have modern society without them, right? Anything that requires a circuit, that kind of work, resistances and currents and stuff like that, you're generally using complex numbers in order to design those circuits. So they're important. They just aren't what we call members of the real number system. Okay, that's what we mean when we say not a real number. So when, oops, what happened to my stuff there? I must have scrolled up. So right here, you would just say it's not a real number, right? Now, we could do this, which is slightly different. If I do this, that's weird. It doesn't usually do this where it keeps dropping us down to the bottom. I don't know why it keeps resetting. But see how here the negative is outside the square root? That's perfectly reasonable, because what you would do is just do the square root part first. Well, the square root of 36 is 6, and then there's this negative in front giving us negative 6. So you want to make sure you understand the difference between these two problems right here, which is the square root of negative 36 and negative the square root of 36. Those are very different from each other, okay? So make sure that you can do those. What about fractions? Fractions are great when you're trying to take square roots. It's way easier than you would think. So let's take a look at that. Let's take the square root of the fraction 9 over 4. And I'm not in math mode. Okay, so see, we've got the square root of 9/4. Well, because of the way that we do fraction multiplication and we just multiply across, that means that these two numbers don't really interact with each other. So we can treat this as the square root of 9 over the square root of 4, which is the convenient thing to do. It's the convenient way to do it, and also it's the right way to do it. So a lot of times, students will look for like an easy way to do a problem, but then it's not mathematically valid. In this case, we get lucky that the easy way we intuitively want to do the problem is actually the easiest way to do the problem as well, right? It's not like some of the stuff I'll show you later where students are kind of trying to take an easier approach actually is not mathematically sound. So, but in this case, it works out. So hold on, I got to mark somebody here. Gotcha. Okay. So the square root of 9 over the square root of 4, you just go, oh, that's not bad. I can make that the fraction square root of 9 over square root of 4. And once we've done that, it's pretty straightforward because square root of 9 is 3 and square root of 4 is 2. And then you're done. 3/2. So that wasn't hard at all. That was pretty straightforward. That was pretty easy to do. And it's easy to check. Is 3/2 times 3/2 9/4? Yeah, that makes sense. Okay. So we're good to go with fractions. Aren't scary. They might scare you, but they're not scary in this setting, right? So when you take the square root of a perfect square, you get an integer. So like we saw up here, the square root of 36 is 6. That means 36 is a perfect square. When you take the square root of a non-perfect square, you get an irrational number, which is an infinite non-repeating decimal expansion, which means you don't really want to write it as a decimal. So like square root of 7, The reason we write it as square root of 7 is because there is not a good decimal way of writing that number. You can approximate it, but it's not equal to square root of 7. It's a little bit different. Okay, so keep that in mind. Right. We don't need to graph those. Now, it can be the case. What about cube roots? Right. Let's take a look at cube roots for a second. Let's do this. So if I've got square root, cube root of -8 equals. Okay, so what's going on here as soon as it compiles? Okay, the cube root of -8. So see this little 3 here now? That's what we call the index. Now, the problems we've all done so far have an index of 2. And you might say, well, I don't see a 2 on any of these. That's because when the index is 2, we always assume the index is 2. So when no index is written there, it's understood to be a 2, which means it's a square root. The vast majority of roots that people run across when they're doing mathematics are square roots. It happens a ton, okay? There are times where cube roots and the other ones come up, but they are definitely in the tiny exception, right? They're not the norm at all. So that's why we just say, well, when we don't write a number there, we're just going to assume it's a square root like we did here. But you get down to here and you want a cube root. That does happen from time to time. You're really just doing the same type of problem, but one dimension higher. So you're saying instead of what number times itself, like up here, we were asking what number times itself gives me 36. Here you're saying what number times itself and then times itself again gives me -8. Okay, so that's what the cube root does. If it was a fourth root, then you'd say, what number do I multiply 4 times in order to get this number? You just go through that process. So here we're saying, what number gets multiplied 3 times and gives me -8? Well, it must be pretty small. If there's a number that I can multiply by itself and multiply by itself again, and it's still only -8, that number must have started pretty small. And so you just try some. People are so afraid to get in there and try it, and then the person next to them is like 5 problems further because they just dove into it and like worked out the problem. Because most of these problems are small. We're not going to give you numbers like 8 to the 9th power or something like that. The numbers just get way, way too big. So try to think small. Okay, let me see. We've got right here. Okay. All right, so in other words, let's see. Is there a number that times itself and times itself again gives me -8? Well, what about -2? -2 times -2 is +4 times -2 is -8. So in fact, yes, we would get -2 would be the answer for the cube root of -8. So notice that cube roots we can take cube roots of negative numbers, but remember we can't take square roots of negative numbers. Oh man, what a pain. So just remember, if your index is even, then you're going to be in this situation. So if your index is like it was here, a 2 that we don't write, or if your index was a 4 or a 6 or an 8 or something like that, then you cannot take the square root of a negative because you're going to run into that same parity problem we ran into earlier, where whenever you have pairs of numbers multiplying, the signs cancel each other out if it's the same number again and again. Whereas down here you have an odd number. Here we have 3 numbers multiplying each other. You can end up with a negative answer. So you just want to be aware of that index is sort of, it makes a big difference. Okay. Right. Okay, so how do we go about simplifying these kinds of things? How do we simplify something? And we're going to look at a lot of simplifying today. I kind of got to keep moving. Although if there's questions, feel free to ask. But we want to start to now make sense of what was up with that fractional exponents that I was talking about at the beginning of class. So let's go here. I just got to make sure I put stuff in the right place here. So there's two versions you can use of this formula. And you should use whichever one is most convenient, because if you use the wrong one, it can make the problem like way, way harder than it needs to be. So this one we'll put here and go. Okay, so what are the keys here? When we have a fractional exponent, the numerator becomes the power that you're going to raise your answer to, and the denominator becomes the index of the root that you're going to take. So a to the mn can be interpreted as the nth root of a to the m. It can also be interpreted as the nth root of a raised to the m. In other words, you can raise this to a power at the beginning. That can be the first thing you do. It can be step 1, or it can be step 2. It can be the last thing you do. The order in which you do these two steps doesn't matter. So both of these formulas hold, and really the question becomes which one's easier for the problem that you're doing. I would say 90% of the time you want to use this second version, and then every once in a while this first version is more convenient to use. But usually it's going to be that second version, okay? So let's take a look at what this would look like. What would it be like to have 8 raised to the two-thirds? So 8 to the 2/3. I mean, that just sounds bizarre at first, right? If you're falling back on our definition of what an exponent is, like x to the 5th is easy. That's just we multiply 5 x's together. X to the 5th, no problem. But what is 8 to the 2/3? I'm going to take 2/3 of an 8 and multiply it by itself. What on earth does that even mean? I don't know what that means. So we use these definitions to put it into place. So what I'm saying is we probably want to use the second definition first. The reason being, if we use this second definition, the answer we start with gets smaller, and then when we raise it to a power, it gets bigger again. If you use this version, which you have to use sometimes, but a lot of times you can avoid it, what happens is you first take the power of something, which makes it really big, and it might make it big to be a number that you're not familiar with, like maybe a 4 or 5 digit number that's so big, and then you're trying to figure out the root of that new number that you're not familiar with. It's like a lot of work, or at least it's more work, so you have to be careful about that. So here's how I would interpret this problem. I'm going to interpret it in the second way, and we're going to make this is going to be the nth root. So it's the denominator gives you the index of your root, so it's going to be the cube root of -8. I put those in the wrong place. No, that's right. So the cube root of -8 squared. So remember, look at it in terms of the denominator becomes the index on your root, and the power becomes the exponent, okay? So then I look at this and go, okay, well, the cube root of -8, oh, we did that up here, right? It's -2. So this would become equals -2 squared, which of course is 4. So we can see that 8 to the 2/3 equals 4. Okay, which seems weird at first, but you'll get much more comfortable with it over time. Okay, so let's do another one just so you can kind of see how this works. Sorry, it's trying to autocomplete my stuff, and I don't want it to do that because it's not doing it right. Is that going to do it? Almost. Here we go. So 32 to the 2/5. Okay, what is that? Well, at first you might go, man, I don't know. That's confusing. Okay, so just go with the interpretation from those rules that we were looking at. So by doing that, that's going to give me the 5th root of 32, and we're going to raise all of that to the 2nd power. Okay, notice how the 2 is on the outside. I should probably put parentheses here just so no one thinks that we should be doing that part first. Okay, so then you go, the 5th root of 32, I don't know that. But again, it's probably pretty small because if I multiply a number 5 times and it's still only 32, it must have been pretty small to begin with. And the answer is it ends up being 2, right? You get 2, 4, 8, 16, 32. 2 to the 5th is 32. So this inside part is really 2. So this equals 2 squared, which again is 4. It's just coincidence both of these came out to be 4. It keeps getting rid of my $sign here in the code. I don't know why it keeps doing that. Okay? Does that make sense how you do that? So I know a lot of time, and write these down. I see a lot of students will call me over for help, and they're like, oh, I get the idea of what I'm supposed to do, but I can't figure out what to do. And then they have like a blank paper in front of them. Don't be doing this in your head. Write it down. Okay, by all means, but you should be writing it down. Okay, so then you just, you'll get comfortable. You'll have problems where you have to do those fractional exponents and go through them from there. And then you'll have problems where they're going to mix these back in with your regular rules of exponents. So you're not just going to be dealing with fractional rules of exponents. They're going to be throwing in negative rules of exponents. Remember, for the negative exponent, you move it to the other part of the fraction and make it positive. So in other words, if I had something like the following. Okay, so let's say we had this problem where we've got some positive exponents, some negative exponents. We got to deal with all of them. Well, what I'm going to do is you move the term with a negative exponent, you move it to the other part of the fraction, and it becomes positive. So I would move the, let me just recopy this thing over. There's a lot to type here. So y to the negative 3, I would move that to the bottom and make it positive, so then we would end up with a y cubed down on the bottom. And then the x to the negative 5, we would move that to the top, and it would become positive. What was it? So x to the 5th. That's not right yet. Hold on a second. Okay, so see how I have no more negative exponents? This y to the negative 3 got moved to the bottom and became positive. This x to the negative 5 moved to the top and became positive. And then we could go ahead and use those previous rules of exponents to make this equal to, be what, x to the 7th and y to the 10th, to simplify that down. Okay, so you have to remember your rational exponents, which we learned today, negative exponents, which I just reviewed quickly, And then your rules of exponents, which we took a real brief look at earlier, but there's all those videos on Canvas to help you remember if you have forgotten how to do that. Okay? So then you'll have a series of questions about simplifying exponents, and you'll want to, follow along the videos. So what happens when we get to something like the following? Sometimes it doesn't render these correctly, so hopefully it's going to. That's actually my fault. Let me see. There we go. So here we have no, it's not rendering it right. We got the cube root of the square root of x. Anyways, we have a square root of a cube root here, right? And we want to know, what am I supposed to do with that? Well, the key is that you would write it in the rational exponent form. So those fractional exponents, like, it's really hard to think your way through them when they're in this kind of symbol version. But when you turn it into rational exponents, then it's just like all those simplify those exponents problems. You just do it, and then you get your answer. So this would actually be, if we converted it, this would be equals x to the 1/3 and that's all going to be raised to the 1/2 Okay, so the x to the 1/3, that's the cube root of x, and then the square root of that is the 1/2 part, right? An exponent of 1/2 is the same as a square root. Exponent of 1/3 is the same as a cube root, and so on. Okay, so then what you would do is go, oh, well, I know my rules of exponents say I'm supposed to multiply these values together. So that's going to become x to the 1/6. Okay, and then as far as the delta math, just pay attention. Do they want the answer to come back in fractional exponent form, or do they want it written with the roots? You just have to pay attention to how you're doing that. Okay, so you'll see a few problems like that. When it comes to multiplying roots, it pretty much works like you would expect it to. You can combine and separate roots with respect to multiplication, but you cannot do it for addition. You cannot split up a square root for addition. So in other words, we could do the following. The square root of 25 times the square root of 4. We'll think of it this way. That's really going to be the number 5 times the number 2, which is 10. Or if we think of it as one big problem, we've got the square root of 25 times 4, which would be the square root of 100, which we know is 10. So see, in this case, you get the same number either way. So that means we can break up and combine our square roots with respect to multiplication. The problem comes in is that people try to split and combine square roots with respect to addition, and it doesn't work that way, right? So let's do an example. If I've got the square root of 36 plus 64 versus the square root of 36 plus the square root of 64. You see, like we'll see here in a second as it renders, this is the difference of what I'm talking about. Up here, we could take two things being multiplied inside the root and just multiply their roots together. So it would be reasonable for you to say, well, can't I do the same with addition? Can't I just split this root up and take the sum of the two roots? And the answer is no, because we'll see that up here, this becomes the square root of 100, which equals 10. But what happens down here? Well, the square root of 36 is 6, and the square root of 64 is 8, so this whole thing becomes 14. So it's clear that we get a different answer when we calculate it these different ways, meaning one of them is wrong. And it's this, like, I mean, these are two separate problems. You can't expect to get the same thing. So don't take this first version and turn it into the second version, or don't take the second version and turn it into the first version, because it's not a legal move. Okay, you're not allowed to do that. It doesn't work that way. Okay, so don't do that with respect to addition. It definitely throws people off. So we want to be careful about that. Okay, then how do we go about simplifying roots? What do we do? What do we do when I've got something like the square root of 12? I want to simplify this thing down. What am I supposed to do? Well, what you're going to do is you're going to look for the largest perfect square that divides 12. So there's not that many of them, less than 12. So you just start going through them. Let's see. 1's a perfect square, but it's not usually that helpful to us. Okay, what about the next one is 4. 4 is a perfect square. Oh, yeah, 4 divides 12. 4 divides 12. Okay, is there anything bigger? Let's see. 6 divides 12, but it's not a perfect square. 12 is not a perfect square. It looks like 4 is the biggest one. So you're going to break the square root up into two pieces. The first piece will be the biggest square that divides that number. And the second piece is whatever your leftover junk is. Okay, just whatever's the leftover. All right, so this equals the square root of 4 times the square root of 3. Okay? Now the reason we break it up into a perfect square and a non-perfect square is that we can simplify the perfect square. So you go, oh, I know what square root of 4 is. Square root of 4 is just 2. So this equals 2 times the square root of 3. Okay? So the square root of 12 simplifies to 2 times the square root of 3. That's the simplified version. Okay? Now here's what people do sometimes is, they'll ask me for help, and they're doing this. They go, okay, well, I've got the square root of 12. Okay? And then you're telling me to break this up into smaller numbers, so I'm going to make it the square root of 6 and the square root of 2. And then they're like, I'm stuck. I don't get it. Why does it not work when I do it? It's because you forgot about the part about the perfect square. It doesn't do us any good to break this down as the square root of 6 times the square root of 2 because we can't simplify either one of those numbers. So this step did not help us in any way, right? You have to break it down where one of them will be simplifiable, meaning that the thing inside the square root is a perfect square, okay? That it's perfectly in there. All right, so that's important to know how to do that. So let's look at another one. Let's look at the square root of 18. So the square root of 18, I go, okay, I want to start thinking about my perfect squares. And the perfect squares, you can learn them very quickly, right? You can make a list of them. 1's a perfect square because it's 1 times 1. 4 is a perfect square because it's 2 times 2. You literally just go through the integers and square them. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. And you have a list of perfect squares, right? 4 squared is 16. 5 squared is 25. And you get all these. So you're like, okay, from my list of perfect squares that I've got, I want to know what's the biggest number that divides 18? Well, 9 is a perfect square because it's 3 times 3. So why don't I break this up as the square root of 9 times the square root of 2. And this gives us, well, the square root of 9 is 3. So that gives us 3 times the square root of 2. And we've now simplified that answer. So the square root of 18 is best written as 3 times the square root of 2. Okay? So that's how you'll go through and do those types of simplifying. Okay. So what about when we get to adding and subtracting roots? Well, now it starts to get a little bit more confusing because square roots operate more or less like terms. So remember how like terms worked, right? When we're adding and subtracting things, we're really just counting how many of those things we have. So if I've got, 5 apples plus 2 apples, this equals 7 apples, right? That's pretty straightforward, 7 apples. And think of the apples as being your unit. Notice how the unit's not changing. People try to do weird things with units when they're adding or subtracting or multiplying or dividing. It's just I got 5 apples in one hand, I got 2 apples in the other, I got a total of 7 apples, okay? So that transforms like when we're doing our polynomial work, things like 5x plus 2x equals 7x, right? Again, it doesn't become like an x squared or anything like that. It's not 7x squared. It's just 7x because I've got 5 x's over here. I've got 2 more x's over here. I have a total of 7 x's. We're just counting them. Okay? Well, it's the same thing if I've got, well, in one hand, I've got 5 square roots of 3. And then in my other hand, I have 2 more square roots of 3. So how many square roots of 3 do I have? Well, I've got 5 square roots of 3 plus 2 more square roots of 3. Then I have 7 square roots of 3. Okay, we're just counting how many of the things we have. It shouldn't be changing the thing itself. Okay, so I've got 7 square roots of 3. So just like when we have 5x plus 2y, we can't add those together. Well, if we have, for instance, let me write this out. So this is similar. If I have 5x plus 2y, we can't really simplify that. We don't have 7 of anything, right? That would be like if we had 5 apples plus 2 bananas, however you spell bananas. Is that right? 5 apples plus 2 bananas. We don't have 7 of anything, right? You could maybe say like foods, 7 foods, but that would be kind of silly. We've got 5 apples plus 2 bananas. There's no way to simplify that. Just like 5x plus 2x, there's no way to simplify that. So with roots, if we have 5 square roots of 3, and I add to it 2 square roots of 7, well, I still don't have 7 of anything, right? I've got some square root of 3s in this hand and some square root of 7s in this other hand, but they're different. I'm not able to combine or simplify those. I'm not able to count them as anything because they are different types of objects. Now, with that being said, some of you are going to not like this next problem because at first it's going to look like I'm contradicting everything I just said, but I'll explain why it's not. So let's say we want to do the following problem. The square root of 75 plus the square root of 27. Okay. And you go, well, that's easy. You just told us if the square roots are different, then I can't combine them. So I'm done, right? Problem over. That was like the easiest one ever. We don't have to do anything. We have to be careful, though, because these square roots are not fully simplified. And the problem I just showed you, square root of 3 cannot be simplified. Square root of 7 cannot be simplified. What you have to do before you decide if these numbers can be combined by addition or subtraction is you first have to simplify them. So the way we did up here with the 12 and the 18, how we simplified these down, that's what we have to do down here in this problem with this thing. So what do? I go, well, what's the biggest square that divides 75? Looks like it's 25. So I'm going to break this first one down into the square root of 25. Yeah, that's right. Sorry, for a second I thought that was wrong. Square root of 25 times the square root of 3 plus, okay, square root of 27. What's the biggest square root that divides 27? 9. Okay, so that's going to give me the square root of 9 times the square root of 3. Oh, I guess I still have more room to type up here. Okay, so some of you are starting to see where this is going to go. Well, the square root of 25 is 5, so the first term becomes 5 times the square root of 3. And then the second term is 27. So the square root of 9 is 3, so that becomes plus 3 times the square root of 3. And look what's happened. We started off with a problem where the square roots did not match each other, but now they do match each other. So we can, in fact, add these. 5 square root of 3 plus 8 square root of 3 is going to be 8 square root of 3. 8 square root of 3 there, okay? So that's how you're going to do that. So you can't just first look at it and go, oh, they're different numbers. We can't combine these. You have to wait and really see, you have to simplify them and then see if their simplified versions are equal to each other or not. Okay? Right. Okay, multiplying and dividing. These aren't terribly bad. Most of the multiplying that you're going to do, you'll just model after how you multiplied polynomials. Okay, so for example, the distributive property. We use the distributive property for multiplying polynomials. We will also use it here. So let's say I've got the square root of 2 times 3 plus 2 times the square root of 5. Okay, so you look at this and you go, probably you're going, oh, that looks like a distributive property problem. Yeah. You're going to distribute the square root of 2 into the first term. Then you're going to distribute the square root of 2 into the second term. And then you're going to simplify those things, and then you're going to be done. So the first part will become 3 times the square root of 2. And then plus, we're going to have what? 2 times the square root of 10. Right? Remember, I can multiply those numbers together that are inside the square roots. That's fine. It's addition where we can't just combine them easily. Oops, I'm missing an equal sign. Looks bad without that, besides being wrong. That looks a little bit better. Okay, so then we end up, well, this is as simplified as it can get. Square root of 10 we can't really simplify, and square root of 2 can't be simplified, so this is as good as it gets. Okay, So like you'll do problems where you have like two sets of, like we had binomial times binomial with polynomials. Here you'll have terms. You're going to use FOIL just like you would before. So if you're looking at something thinking like, ooh, should I use FOIL? Yes, probably. If it looks like it works for that. So the multiplication is pretty straightforward. If you're stuck, watch some videos on the delta math. You'll pick it up very quickly. You'll be just fine. Then we run into something which is called rationalizing denominators. And rationalizing a denominator means that we want the denominator to be a rational number. So rational in mathematics, remember, means like fraction, basically. It means we have a ratio, rational ratio. That's where it comes from. And a ratio can be written as a fraction. Okay, but this sometimes gets forgotten. A fraction is technically a fraction of integers. You can't like have a fraction of decimals. I mean, you can write the fraction as a decimal. We almost never do that. You can do it, except it's a really sloppy way of doing it. And then that number technically is not a fraction anymore. Right? We might use the word fraction, but a fraction is defined as an integer over an integer. So what does that mean for us when we're trying to do this? Well, the directions to rationalize mean that we want that part of the fraction to be able to be written as a fraction. So it's you'd think of it as a fraction and a fraction, but generally it comes out as an integer. But we don't like both of parts of our problem to be written as irrational numbers. So let me explain what I'm talking about with an example. Show you what I mean here. Let's start with a simple one. So square root of 5 over square root of 3. So square root of 5 over square root of 3. Now, if the directions say rationalize the numerator, you'll do everything we're doing. You'll just flip it so that the numerator is the thing getting rationalized. Oftentimes, we want to rationalize the denominator. So I'm showing you how to do that, where we go through and rationalize the denominator. So basically what you're going to do is look at the denominator and ask yourself, what do I need to multiply to get that thing to be an integer? And if you're dealing with square roots, then you're just going to be multiplying that thing by itself. If you're getting into cube roots and fourth roots, it can get a little bit trickier. It's not bad, but you have to think a little bit more. But if it's square roots, you just multiply the thing by itself. So I want to multiply this by square root of 3 over square root of 3. So it looks like this. And then what's going to happen when I multiply across, I'm going to get square root of 15 on top. And I'm going to get 3 on the bottom. And 3 is a rational number, so we have rationalized the denominator. That's what that means when we say that. Okay, see how we did that? You might go, well, I don't know. It just doesn't seem like we made things that much better. We didn't make them significantly better, but we followed the directions of rationalizing the denominator, and a lot of people would argue that that's better, right? A rationalized denominator is better than a non-rationalized denominator because it's easier to understand. I can understand square root of 15 divided by 3 better than I can understand the square root of 5 divided by the square root of 3. I don't know what that comes out to be. Here I could kind of make a guess a little bit and be able to ballpark it a little bit. So it's a simpler version. We always want to be simplifying things. Okay, and then it gets slightly more complicated. So what if I wanted to do the following problem? Say I've got square root of 2 plus 3 over the square root of 5 plus 7. Okay, so when we have this, remember I told you that when you take the square root of a non-perfect square, you get an irrational number, right? So when we have a fraction with irrationals in it like this, we can't rationalize both the numerator and the denominator. It's one or the other. Pick the one you want rationalized, and we can do that one. Frequently, you want to rationalize the denominator. So how do we do it here, though? This is a little confusing. If I just multiply by square root of 5 plus 7, I don't think it's going to come out right. So what do? The answer is this thing called the conjugate. So you first saw this when we had, when we did our factoring and we did difference of squares formula, you have this pattern of two things being added together times those same two things being subtracted. That is a pattern that we make use of in mathematics frequently, and it gives rise to what we call the conjugate. So the conjugate is where you take the expression and you change the sign in the middle. And a lot of times people go, oh, you mean multiply by -1? No, I don't, because here's why. So it's going to be what? It's going to be the square root of 5 minus 7. Okay, so we're multiplying the top and bottom by the square root of 5 minus 7. That's the conjugate. And people go, yeah, you multiplied by -1. No, if I multiplied by -1, it would be negative square root of 5 minus 7. That's not what we have. We have square root of 5 minus 7. You are only changing the sign between those two terms. That's called the conjugate. Now, a weird thing happens when you take the conjugate that's really convenient. It's the reason that difference of squares is such an easy formula to use, because a bunch of it cancels out and makes our lives easier. It's the same thing that's going to happen here. That's why we're using this form. So let me kind of write off to the side. This is one where I like to kind of do a little bit of side work to figure out my answers. So let's see. Let's just look at the numerator. Okay, so the numerator is going to be So numerator is square root of 2 plus 3 times the square root of 5 plus 7. Now I told you a minute ago about FOIL. This is where we're going to use the FOIL. When you have 2 terms times 2 terms, we're using FOIL just like we did for polynomials, right? So if I do my FOIL, I'm going to get square root of 2 times square root of 5 is square root of 10. That's my F part, my first. Okay, outer, I'm going to get 7 times the square root of 2. Okay, that's my, oops, should have a plus in here, huh? Plus. Okay, now my inner is going to be what? 3 times the square root of 5. And then my last, the L part of my FOIL is going to be 3 times 7, which is plus 21. And there's no simplifying we can do here, right? That's as simplified as we can get. There's no square roots that are the same that we could combine. That's what we're stuck with for the numerator. So I'm going to take this, and we're going to put it on top. Now we're going to figure out the denominator. Okay, so let's do that. So we've got what? Square root of 5 plus 7. And and square root of 5 minus 7. All right, so I'm going to FOIL. Square root of 5 times square root of 5 is 5, right? Sometimes people get lost on this. There's two ways to think about it. Square root of 5 times square root of 5 by definition is 5. But also if you want to use the multiplication rule, some people like have trouble with that definitional view. Square root of 5 times square root of 5 is square root of 25, which is 5. So you can either do it directly from the definition or indirectly using the multiplication. Either way, you get the F part of your FOIL is just the number 5 here. Okay? Now we do our outer. When I do the outer part of my FOIL, I get negative 7 times the square root of 5. So minus 7 times the square root of 5. Okay, that's fine. Now what about my inner? That's going to be 7 times the square root of 5. So plus 7 times the square root of 5. Okay. Excuse me. And then I have 7 times negative 7, which is negative 49. So I get this. And you kind of go, okay, big deal. But look at this. We have some work to do. Look at our middle two terms. I have negative square root of 7 plus 5 plus negative 7 times the square root of 5. Is that what I said, or did I say it wrong? Negative 7 times the square root of 5 plus 7 times the square root of 5. Those cancel, and they become 0. So your middle two terms cancel each other out. Right? And then we're left with what? 5 minus 49. So this whole thing becomes negative 44. So we have rationalized the denominator, because our denominator, and remember back in our original problem, the denominator is now negative 44. You could argue, well, this seems more complicated than what we started with. Look at that numerator. It's a mess. Yeah, the numerator is kind of a mess, but the denominator is real clean, right? In fact, we probably wouldn't even leave that negative in the bottom. We'd move it to the top, or we'd move it out in front or something, because we also don't like having negatives in the denominator, right? But that's fairly easy to fix. So this side work here takes a little bit of effort in order to figure these out, right? So you'll be getting those multiplications done at the same time that you're rationalizing and doing these other steps. Okay. All right. Then we get into radical equations, which I have videos posted because I'm probably only going to be able to get through one problem here. But I have videos posted on Canvas, and YouTube's full of other videos of other people doing these same problems. But I would say work through mine. They're quick. You can see the steps that I'm taking and figure out how to do it. So let's work through one of these quickly. Let's do this one. Okay, so I've got the steps I'm going to tell you hold no matter what problem you're working on. Sometimes you have to do a few extra steps, but it's the same basic idea. The equations will change, but the same basic procedure holds. So watch those videos that I posted. So we've got this, there we go. The square root of x plus 3 equals 4. How would I go about solving this? Step 1 is to get your square root isolated all by itself. In this case, we already have that because the square root of x plus 3 is by itself. Great. Step 1's already done. If it isn't, then just get the square root isolated by itself by either adding or subtracting, whatever you need to do to get that square root isolated, okay? All right, we got that. The next step, to undo a square root, you're going to square both sides. So when I square both sides, I'm getting when you square a square root, you just get what's inside, right? So this becomes x plus 3. And then when you square the right side, 4 squared is 16. And then when you subtract 3, you get x equals 13. Now, these are pretty easy to check. Look, we're not even going to have to write anything down to check it. All right, x equals 13. Did I do that right? Well, let's go plug 13 in here. The square root of 13 plus 3 would be the square root of 16. Square root of 16 is 4. Okay, so 4. So that's true. 4 equals 4. So we're good to go. Okay. So that's how you do that one. In fact, maybe I can sneak another one in here. Let's do this other one, because this next one is where most people mess up. Most people can do problems like this, but let me do another one. So I'll try to move quickly enough that I don't go over time. Let's see. Square root of 3x plus 1 plus 1 equals x. Okay, so we've got the square root of 3x plus 1 plus 1. See how the plus 1 is outside of the square root here? Equals x. Okay, so remember step 1 was to isolate that square root by itself. Well, we don't have that now. In the last problem, we started off with the square root isolated, but here we don't. So what do? I'm going to subtract that 1, this 1 out here by itself. I'm going to subtract that from both sides. So what will happen is that we'll get the square root of 3x plus 1 equals x minus 1, because I'm subtracting 1 from both sides of the equation. So that means on the right, I now have x minus 1. Okay. Step 2 now is going to be to square both sides. The left side, most people are fine with. When you square the square root of 3x plus 1, you get 3x plus 1. And here is where 90% of the mistakes get made when doing this type of problem. People look at that right side and go, okay, now it's my turn to square x minus 1. And what they do is they make it x squared minus 1 squared, or some version of that. They'll do x squared plus negative 1 squared or something like that. When you square things, when you square a sum, you cannot square each term individually. We did this in when we were dealing with polynomial multiplication. We looked at that intensely, and then people forget how to do it. So remember, when I square both sides, the right side actually should look like this. X minus 1 times x minus 1. That's what x minus 1 squared means, is you multiply it by itself. You don't get the same thing by just squaring the x and just squaring the 1. It doesn't work the same way. Okay? So what this would become then is 3x plus 1 equals x squared. So your outer would be minus x and your inner would be minus x. When you combine those, you get minus 2x. And then when you do the L part of your FOIL, negative 1 times negative 1 is plus 1. So I'm running out of time, so I'm not going to finish this problem, but we did the part that confuses people. From here, you would just finish this problem the same way you did when we covered factoring polynomials and then solving equations using factoring. That's just what you'll do here. It's the new step is this beginning piece. So you get the square root isolated, then you square both sides, but you have to square this right side correctly, right? That's usually where the mistake gets made, if there is one. Now, that's how you'll do all of these square root problems. Now, what if your problem has a cube root in it? I don't think those come up in the homework, but they come up sometimes like in life. Well, then you would cube both sides, right? You're doing whatever undoes the root that you're looking at. You're trying to get rid of that radical, okay? So you've got some homework due today. So please make sure you get that homework done. Remember, you can always work on homework late, but it's only worth half credit, and you might as well get full credit, especially if you're going to do the work anyways. And then we've got this new stuff. Now, I didn't get into radical equations, but I think that's okay because I've got the videos, and the videos would basically be exactly what I would have gone over in class. So if you go into radical equations, you've got videos right here of me working out these kinds of problems. So you can watch me do 4 different difficulties of these problems. Okay? So you should be good to go with those. And then it looks like the homework's maybe due in a week. So try to get that stuff done by the time you get there, and then we can move ahead. Okay? So we're plowing through these things. We're learning all this algebra. We're getting closer and closer to the part where we get to just focus on the dosages, right? How do we safely administer medications to people? We're going to get there, but we still have some of this groundwork to get through along the way. Okay, so keep up the good work. I'm going to close down the YouTube stream. Anyone who wants to talk to me, either to ask me questions or comments or concerns or anything like that, please stick around in Zoom, and I will talk to whoever needs to talk to me for as long as you like. We can chat about whatever is a concern for you. Otherwise, I will see you in a week. Please make sure you're staying on top of the homework and that you're good to go. Good work, everybody. I'll see you in a week. Thank you.